In 1819, Hans Christian Ørsted just made a discovery. In 1819, he made the discovery that we said was probably, if not the most, but certainly one of the most important technological discoveries in the history of the world. He discovered that moving electric charges generate magnetism. In other words, you got an electric current, you make magnetism. Electric current generates magnetism, or generates a magnetic field. 12 years later, two guys, an American and a British guy, independently of one another in 1831, both discovered the complementary effect here. Not that electrons moving generate magnetism, but rather magnetism can generate moving electrons. Magnetism can generate electric current. That's what we call the generator effect, the production of electricity from magnetism. Remember, the motor effect, which is Ørsted's discovery, the motor effect says that we can generate magnetism from electricity. The generator effect says that we can generate electricity from magnetism. We can produce electricity. This is a basic principle, by the way, behind just about every electrical generation station that we have out there. The exception to it would be solar power. It doesn't work on this principle at all. But wind power, hydropower, coal-fired power plants, natural gas-fired power plants, nuclear power plants, they all work on this basic principle that we make electricity from magnetism. It's discovered in 1831, as we said, by two different guys, independent of one another, Michael Faraday and Joseph Henry. Recognize that name? Where did we see that before? In the Faraday cage, right? That's the idea that you can't have an electric field inside a metal cage. Now, in order for this to happen, it's not quite as simple as Ørsted's discovery. Ørsted said, look, anytime you have moving charges, you will generate a magnetic field, no matter what, every time. But with Faraday and Henry's discovery, it's not quite that simple. You can make electricity from magnetism, but certain conditions must be met for that to happen. There are no conditions for Ørsted's discovery. Every time, electricity will generate magnetism. But magnetism will only generate electricity under certain conditions. You need a conductor in a magnetic field. So in other words, you need a wire and a magnet. Given a wire and a magnet, one of the following must occur. You can move the wire. If you've got a magnet and a wire and you move the wire, that will generate a current in the wire. Or you can move the magnet. So it doesn't matter which one moves, as long as either the magnet or the wire move relative to the other one, then you generate a current. This is how all the power plants work, right? Water goes through a dam, goes through this penstock, it's called, turns a turbine. What happens really? Well, you're moving a whole bunch of wire, a whole bunch of coils of wire relative to a magnet, and you generate a current in it. When you use nuclear energy to generate electrical power, you split the atom, it generates a whole lot of heat, which boils water, which turns into steam, which rises, turns a turbine, which consists of wire that moves around a magnetic field, generates an electric current. When we have a wind power, right? Wind blows the turbine, which consists of wire that moves now that the turbine is moving around a magnetic field, which generates an electric current. They all work on the same basic principle. You've got a conductor and you've got a magnetic field, and one of them moves. One of them moves because of outside energy, whether it be kinetic energy from the steam rising, or kinetic energy from the water that falls, or whether it's kinetic energy from the wind that blows. It turns a turbine, generates electricity. Now the third way, we don't deal with this very much in Physics 30, but you can actually generate a current if you change the magnitude of the magnetic field. So if you strengthen and or weaken the magnetic field, you can also generate a current. But we're going to focus on these first two for sure. There's a picture up on the board right now. Hopefully nobody's colorblind, because I'm going to color code some things here. Green is going to be the direction of, or green is going to be electric current. Right now we have no electric current. Okay? Blue is going to be the magnetic field. We do have a magnetic field that points this way from north to south. Red is going to be the magnetic force. There is no magnetic force right now either. So we have one thing, and that is a magnetic field with a wire in that magnetic field. But no current, no nothing, no battery attached, no nothing here. You've got a wire and a magnetic field. Now, I'm going to push the wire. I'm going to lift the wire upwards. Now, I can do that physically with my hand, or maybe it's steam rising that pushes it upwards, or maybe it's some kind of wind from a turbine that causes it to move upwards. Bottom line is this wire is going to move upwards. Nothing's happened yet, right? We've got a wire that's moving in a magnetic field. Well, we learned a minute ago that that will generate a current, but why? Because inside this wire are protons that can't move anywhere and electrons that can move somewhere. Now, you got to understand that we have electrons in this wire not doing anything yet except moving upwards. Why are they moving upwards? Because we pushed them upwards. Right? Make sense? We push the wire upwards, and of course, the electrons have to go with it. So now we've got moving electrons in a magnetic field. That causes a magnetic force. Moving electrons in a magnetic field causes a force. Let's say thumb in the direction that the particles are moving upwards. Why are they moving upwards? Because we pushed them upwards. Not from some electrical or magnetic effect. We pushed them upwards. But bottom line is they're moving upwards. Fingers in the direction of the magnetic field, which is from north to south. That means on all of these electrons in this wire, there's a magnetic force which way? Into the page. So we have a magnetic force on all of these electrons into the page. What happens to these electrons as a result of that magnetic force? They start moving where? Into the page. What do we call it when electrons are moving through a wire? Conduction, or it's an electric current. So we have an electric current going into the page. We have a magnetic field this way. We push the wire upwards. That generates an electric current into the page because of the magnetic force on these electrons. That's why electrons start moving in the wire, because of the magnetic force. It's ironic, right? What causes electricity? The magnetic force on the electrons in the wire as they move the wire. Does that make sense? That's the generator effect. Okay, Faraday-Henry, as opposed to the motor effect, which was Oersted. Okay? Both of these are pretty important discoveries, right? I would argue that the first one, Oersted, is probably a little bit more important. But if we don't have the generator effect, there's a lot of things a lot of technology that we have today that still doesn't work, right? Make sense?